Welcome to the last session of J4, the dessert so-called, which starts quite nice with the wrong screen. That's no joke, unfortunately. I wish it was. But of course, we are used to troubleshoot. We are engineers. Wow. We made it! At the end of the day, the last challenge has been completed. Welcome again to our last session today, where hopefully I'm going to unlock a lot of mysteries for you regarding generative AI for the GVM platform. My name is Urs Peter. Let's go quickly through that. I'm a daily job. I try to be as much as possible with my hands in the dirt. The older you get, the harder it will be. Remember that one. I'm also a frequent speaker in conferences. If you have visited some of these, you might have seen me. I'm also a passionate trainer, mostly about Kotlin, where I help developers in all stages of their Kotlin journey. No matter whether you're a beginner, intermediate, or advanced Kotlin developer, I can show you the next big thing. Keep that in mind. As such, I'm also a certified JetBrains Kotlin trainer. Enough about me. I would like to know a bit more about you, and especially about your AI usage. So who of you is using ChatGPT more or less on a daily basis? OK, that's about half. OK. Who of you is using an AI coding assistant like Copilot? That's about a third or 40%. OK, cool. Who of you is thinking that AI will take over our jobs? In other words, that we are doomed in the long run? Ooh, quite some pessimists. OK, I don't raise my hand. You maybe will know why at the end of this talk. OK, so if we had to kind of find an analogy for our field of software development prior to this AI hype, we could say that our field was a bit of a predictable environment, a bit like a swimming pool, where we had to deal with more or less well-known aspects of software development, like the ones you see here. I think most of the time we enjoyed what we were doing. Sometimes maybe we encountered a more chilly section, but overall, I would say we could keep our head above water. And then, besides our field, we had this big gap with these kind of terms: data science, neural networks, machine learning. And maybe some of us crossed that bridge. Who of you crossed that bridge? A few. And most probably because you had to, because you had a project where you did something with data science, or you fiddled around yourself. But generally, we could say these were two separate, distinct fields of expertise. Well, with the advent of AI, things started to change a bit. The peaceful waters of our swimming pool got a bit stirred up with all kinds of fancy terms, concepts, techniques, and so on, that somehow demand a reaction from us software developer, because this whole AI thing just came closer. It was not just a gap anymore, it just came closer. So how do we have to deal with it? The aim of this talk is to bring you AI a bit closer in the cozy and well-known realm of the GVM. I actually quite like this picture. Why? Because it nicely reflects the stage, the maturity AI is in right now. When I asked the image generator to generate this image, I said, please depict a truck that unloads a cargo in a pool. There we go. This is probably not how you unload a cargo in a pool. And I'm not the only one having issues with AI. When we see recently what kind of case we had of companies that released some AI-based applications, then they kind of made it to the newspapers or news sites. So for instance, McDonald's had to remove its whole AI order system. Air Canada had to pay a lot to customers, and so on and so on. On a more or less weekly or daily basis, new kind of failures you can read about. OK, when we're talking about generative AI, we're actually talking about these bad boys, the LLMs, large language models. So what are LLMs based on? Well, they are neural networks, which are actually part of the discipline of deep learning. And as such, they are based on the so-called transformer architecture, designed to process and generate data. You probably know how they're created. Well, with a tremendous amount of data, they're created, ideally the whole internet. And this leads to so-called billions of parameters. What are parameters? We're not going to go too much in detail there. They're actually weights or bytes on connection between neurons and other things. But it actually gives an indication of how well your model might perform. So here you see some models and the amount of parameters they have. Mistral, created on European soil in France, has about 7 billion parameters. GPT-3 had 175, and by now we are at 1.8 trillion. So quite a steep increase. What you get then is a GPT, and this stands for, if you didn't know it, for generative, because it generates stuff, pre-trained, because it's trained with a tremendous amount of data, and transformer, because it's based on transformer architecture. So what do LLMs actually do? And this is very important to realize. What do they actually do? Well, what they do is they take an input token and then predict the next most likely token. That's what they do. And as such, they're very good at creating text that sounds nice, but of course is not necessarily right, which leads to these so-called hallucinations. There is a parameter which you can kind of tune the amount of hallucinations, make it more or less hallucinating. So the lower the temperature, the more factual your reply will be, and the higher the temperature, the more wild it will be. So that's for one. And the latest model was released by OpenAI, the so-called O1 strawberry model. So we went from GPT-4 to O1. That's not a typo, that's how they do versioning there. Is a model that is said to be able to good at reasoning. We even pay separately for their reasoning. But remember, all LLMs are based on this concept of predicting the next most likely token. What's also important to realize with LLMs is that they're fully dependent on the data they're fed with. So if your data is erroneous, biased, so will be your responses. For us developers, an LLM is actually just another black box. A black box you can run on your local machine. The command for doing that is here. So if you copy-paste to your machine and you have a bit of gigabyte of RAM, then you can run LLM locally. At least with the Ollama toolsets, you can run open source models. I can give you an example. So here I say, Ollama, run Mistral. Then I can start typing stuff. For instance, I can ask, how good are your reasoning? And it says, yes, I can reason logically based on information provided. OK, that sounds pretty good. So let's just see how well it reasons. How many R are in the word strawberry? The letter R appears twice in the word strawberry. Twice? Maybe it's me. I thought it's more time. OK, let's check. Really? Really, it's just the third and seventh letter are both R's. Well, this is, I think, a nice example of good reasoning, right? I really don't like this screen. Go away. Well, in a production situation, you probably don't want to run your LM on your local machine. You also can run it on your own premise, in the cloud, for instance, which allows you to send sensitive data to it. So for a company, you probably would have your own instance of an LM. But of course, you also can use the open and public LMs, for which you should take care of that you don't send sensitive information. However, for us developers, an LM is actually foremost just another API we have to deal with. And when there are APIs, well, frameworks aren't far, generally. And this is on the GVN. In the GVM field, we have two major frameworks that kind of facilitate the interaction with those LLMs. And this is LangChain4j, which is based, or actually a port of the well-known Python LangChain framework with these kind of features. Maybe by now you think, OK, what is this? Vector stores, embedding models, RAG, ETL, buzzwords you don't probably understand. At the end of the presentation, you should be able to quite clearly name all these different capabilities. Then, kind of competitor, you have Spring AI, which is kind of its own invention of how you should deal with LLMs, which has more or less the same capabilities. So in terms of feature, they're quite comparable. At the end, we'll also look at the differences, but generally we can say they both do more or less the same thing, and it's a bit up to you what you would like to prefer. OK, so how do these frameworks interact with an LM? Let's do that, just to give you a feeling how this works. I will start out with LangChain4j, and that might be a bit confusing. I'm going to do that within a Spring Boot application, because LM has also, LangChain4j has also nice starter jars that allow you to automatically wire some Spring Beans. But beneath, all the objects of LangChain4j would be used. Then I provide some configuration. One of the most important configuration is an API key, because I'm using OpenAPI here. The model, GTP4o Mini, is actually a good one for us developers because it's very cheap and still quite performant. I also have something here like temperature, and then more or less the most important property has been defined. So I just have a controller here. Then let's just add some stuff to it. So this would be a simple chat application. I would use this chat language model object, which would automatically be wired if I have this starter jar. And then I have this template approach, where I have these overloaded methods to pass all kinds of parameters. And this call would simply return a string of the reply. So let's take a look at that. I would have loved to run this real dynamically, but internet connection is not really great at JFall so far, so I just made a move with it. The way this is demoed is within a so-called Kotlin notebook. You will look at them in the mirror, of course, so I will try to incorporate some Kotlin in here, where you simply can execute some code in these coding sections and see the result right away. And you see that if I ask my endpoint now what the coolest Java conference in the Netherlands is, we get the right answer. Woohoo! So they don't do things all the time wrong, these LLMs. If you look closely how the response was given, so let's maybe go back, then you see that it appeared actually all at once, right? So, but then you had the response. When you have very lengthy responses, then this is not a very convenient way to get your replies. So you would actually prefer to have them streamed. That's very simple to implement too. So we would make that this endpoint. You could also use a streaming chat language model, but then you get quite a bit of code you have to create. You also can use one of those assistants. The way this works is you just have an interface, you annotate, and then while starting up, Spring, or then at least the feature LangChain4j offers you with its AI service, would then wire everything for you that you simply pass in the manager, and magically it would call the LLM. The result you get then looks as follows. So I'm going to change my endpoint now to stream, execute it again, and now you will see the responses appear paragraph by paragraph. OK, so now we're going to take a look at how these samples would look like in Spring AI. They look quite similar. We're going to right away look at the example we just did before with streaming. Spring doesn't have this template approach. It has this client approach. So I have a so-called chat client, which I can configure here with some advisors. An advisor is a simple interceptor that intercepts the request and the response when communicating with the LLM. Then you kind of have this builder pattern where you just compose the client as such that it does what you want it to do. So here, say, create a prompt, this would be the message, and stream that message. And the result would be really exactly the same what we've just seen before with the LangChain4j example. So far, so good. What Spring Boot is quite good at is some bit more advanced interactions with LLMs. So for instance, what we can do is converting the result to a certain type. And this is what happens here. So I have this top dishes per kitchen. I would have a kitchen parameter. Then I have this template approach here where I say, give me the most wanted dishes for this kitchen. I have a nice interpolation approach to fill in my kitchen parameter. And then, rather than returning the reply as a string, I can say, return this reply in this particular class. This is just a simple record structure. And quite a few things need to happen for this to work. Spring needs to instruct the LLM in a separate message that it expects the reply in a certain format, which would be a JSON schema. That's literally what Spring Boot would send to the LLM, so that LLM could reply as such. OK, so let's take a look how this is going to look like. We say Italian kitchen, get JSON, again, a nice Kotlin extension method, and all of a sudden we should get the reply, not as a string, but as a nicely application JSON content type. OK, what's also quite cool is that Spring allows us to include media in our prompts. Not all the models would support media. For instance, the Mr. model I showed you locally would not support media, so it's not a multimodal model, so it's called, as it's called. It simply would support text, but the OpenAPI model supports media, and with Spring AI and its client, it's really a piece of cake. You say media, MIME type, and you provide either an input stream or URL or whatever, and then you also can send data to your LLM, which is not text. And what we'd like to do here is to say, detect all the objects in image, considering the URL I provided here as an input. So let's do that and see what happens. Another cool feature of Kotlin Notebook is that you can print HTML. So I have this HTML wrapper, and then, but I see a nice image in here in this notebook. Then I simply call my new endpoint, and I would expect a decent description of what's in this image. And I think it does a pretty good job. OK, so I think by now we have seen that we can do kind of cool stuff. It's nice for demos, but probably in the real world, you wouldn't really make a difference. And of course, we want to make a difference. So how could we make a difference? Well, maybe by implementing something McDonald's tried and miserably failed. Maybe because they started quite early. So in 2019, this project was launched. And there, at that time, I think there wasn't a Spring AI LangChain4j or a decent LM. So let's see if we can do better. But of course, not with fast food, which is unhealthy. We go for a more delightful option, which is an AI-powered Italian restaurant, where based on some menu and ideally some voice interaction, we should be able to order delicious, delightful Italian food. OK, this brings us to our first challenge. How do I incorporate my own data in an LLM conversation? So basically, the menu I need to integrate somehow in LLM. How can I do that? There are actually two approaches to do that. The first approach is called LLM fine-tuning. So what you do is you take an existing LLM, an open source one, then you would somehow add your own data to it. In our case, only menu. If you make something more complex, probably you also need much more data. And then the end is a fine-tuned LLM specifically for your purposes. The drawback is, especially when often you need a lot of data to make it really work, it's very costly. And second, if something changes in your data, your LLM is outdated again. So this approach is actually only beneficial for use cases like our AI coding assistant. For these kind of use cases, such models are created. Or from very specific medical models and so on. This kind of justifies the investment you have to make such a model. However, for enterprises, it's a different story. Then you would make use of this approach. Fancy name, retrieval-augmented generation, RAG. You might have heard it by now sometimes today. Conceptually, it's actually quite simple. How does it work? Well, you have a prompt. Then you take your prompt and look up similar information for that prompt. You get back that information, and you simply would put it into your prompt and send to LLM, so the LLM can use both inputs to do whatever it needs to do. And this has a nice kind of term that I think is really well understandable, stuffing the prompt. That's what we do here. It looks very simple, but there are actually quite a few interesting and complex mechanisms behind it. Think about it. Well, first, we need to somehow ingest data that we can do a search based on similarity. These two aspects we need to take into consideration. And in order to understand how this really works, we need to take a step back and look at natural language processing, in short, NLP. What is NLP? Well, NLP is the capability of computers to understand and generate human language. With that, you can do a lot, but what you can achieve with it is so-called semantic search or similarity search. What is that? It's very simple. If I look for the word king, then also expect replies back that contain words similar to king, like monarch, emperor, and so on. And that's very important. This also applies to whole sentences. So if I provide a whole sentence, I expect content back that somehow reflects my sentence. Fuzzy, right? But language is fuzzy. So how can we do that? It's not that hard, so let's break it down. How can you give meaning to words so that a computer understands it? How can you do that? Well, that's not that hard. What you do is you use so-called n-dimensional vectors. And depending on the model you're using, you have between 300 and 2,000 dimensions. And each dimension represents a characteristic of a word. So let's take the word queen. We see that the first dimension, reality, it scores high, on the second lower, and on the last one, femininity, it scores, of course, high again. So these are so-called weights for a word. The next question would be, how do I get these weights, right? So here again comes training in place. You take a large corpus of text. When you have a lot of text and you train this model, eventually, automatically, these weights should be put right. Because when you have text that is about a queen, then probably it will be in the context of reality, femininity, but not masculinity. But as I said, this depends on the corpus of text you're using. And experience learns, the larger the corpus, the more you will kind of diverge towards general human understanding of language. Once you have actually all those weights defined, you're not really talking about a vector anymore, you're talking about an embedding. Technically, it's slightly different, and it's important to mention that. Why? We're actually not vectorizing words, we are vectorizing tokens. There it is again, tokens. So what the heck is a token? Well, token you get by tokenizing text. So if I have the sentence, the queen rules the kingdom, then I would get these tokens. So why do we do that? Because, that's what you see here, it reduces vocabulary, it captures semantic, and because we have a smaller vocabulary, we also can make our processing more efficient. So what you see here is that king and dumb is actually split into two parts, and the rest is just one-to-one copied. And that really largely depends on how the tokenizer works for a specific model. Then what you would do next is you would assign numbers to your tokens. Like here, queen has number 4,576. And then you actually can look up those numbers in your embedding model and get the meaning. And by doing so, we are back to numbers, and computers like numbers, so they can generate it. What's important, actually, an additional capability we gain with that is that we also can vectorize whole sentences. So instead of taking all the initial tokens of a sentence, you can get one vector for a sentence. How does that work? Again, quite simple. So say we have this sentence again, the queen rules the kingdom. What you get is actually all the initial vectors aggregated as one with different algorithms that can do that. And the result is, again, one vector which depicts the meaning of the sentence. So we see that this sentence scores on masculinity and femininity about 50-50 because both are represented in a sentence. And by doing so, we capture meaning of a sentence in one single vector. Well, that was quite a mouthful, right? Sounded a bit like a lecture. But the cool thing is you can nicely play around with these concepts. And I will do that with tools that are available within LangChain4j. So what I have here is an embedding model. You can look them up. They have fancy names. They also have very specific capabilities. This is just a general purpose model for normal text. I loaded my model here. And now I can create an embedding for a word. So we now create an embedding for the word kingdom. And we see that if you look at the dimensions, it's a model that has 512 dimensions. So decent, not very much decent. And believe me, behind that is a vector. It's just a vector, and it's an array of numbers. That's what's behind. When we look at how many tokens was used for that, we just see that kingdom is split into two, at least in this particular model. We actually expect 2 tokens, right? That's what we see here. So input token is 2. If we now would use another word like king, then we still would have 512 dimensions. We still would have 1 vector, but now we only would have 1 token. And the same is true for if I would use a whole sentence. The king is great. Again, 512, again 1 vector, but more tokens, 4 tokens. Why are we doing this? Well, because it allows us, once we converted text to vectors, to do calculations. And what you can, the most important calculation we try to do is to check the similarity between 2 vectors. That's actually what, on a math point of view, is happening. How does it work? Quite simple. I have 2 texts here, a function that takes 2 texts, text 1, text 2. We create embeddings for each text, and then we use an algorithm called cosine similarity. And again, here also quite a few others are applicable. Cosine is one which is frequently used for text. And by doing so, we now can see how similar is king to queen, and it's quite similar. But if I would use something else, like phone, probably that wouldn't be that similar. And again, important to remember, it also applies to all sentences. So the king is in the capital, the queen is on the throne, 0.5. If I would say the best part of Java, just a very arbitrary sentence, then we would see that they are not very similar. Okay, that's all nice and fancy, but how can we now incorporate these techniques in application to make something useful? Well, what we need to do is the following. So we take, in our particular case, our menu, and then we would use a process to create some text that we will create embeddings for. And the text we create for the embedding is up to us. So in this particular case, we'd use maybe the menu name, the category, and some ingredients. We would then ingest this into a database, because eventually I need to query something. Once I have this in place, I could use a prompt, again vectorize it, and then it's vectors against vectors. I could do then a similarity search, similar to what we've just seen with our cosine similarity. And this is actually what we're going to do next. But before we're going to do it, we need to understand a bit more about those vector databases. So who of you knows what a vector database is? Some, but definitely only a few. OK, cool. So we're probably going to learn something new today. Well, guess what? A vector database is a database that stores vectors. That's kind of logical. And of course, corresponding metadata. The advantage of having data as vectors allows us to do quite a lot of cool things, like the ones you see here. We are interested in the similarity and semantic search. Because what you can do is, if, for instance, we had vectors which only have 2 dimensions, for simplicity, because then I can show it to you. 512 dimensions is a bit hard to show on a slide. That doesn't fit in the human brain, but 2 dimensions fit. So if I have all these vectorized data, then I could have a query, which also vectorized. Then I could actually query the k nearest neighbors with that k nearest neighbor algorithm. And by doing so, I get similar things back, right? The only problem with KNN is that it's very resource intensive. So it can really take up to hours to do a decent search. It's very accurate, but it's resource intensive. So vector database, they came up with a solution for that. Guess what? They use indexes, specialized indexes for vectors. And an index you will frequently see, which probably for now is abacadabra, but once you're a bit more in that space, you will see this more frequently. HNSW is an index that is frequently used for vectors that are text-based. You also can vectorize images, videos, you can vectorize everything, but for text, this is a good index. What is the impact of using index? Well, conceptually, this works as follows. So instead of doing this k nearest search, we now can do a so-called approximate nearest neighbor search. Approximate, right? That's not that accurate, apparently. It's approximate. So a vector database actually clusters its vectors. And whenever you have a query, your query would land in one of those clusters, which is closest to what this query represents. And then all the elements in this cluster you would get back, whereas elements that are outside of your cluster, you wouldn't get back. And that's why it's called approximate. And of course, the advantage is that it's very fast. So you trade speed versus accuracy. There are quite a few vector databases out there. And what's cool to see is that many traditional databases also add some vector extension, because it's actually not so hard to do, right? There's not a lot of magic involved. Implement this call sign similarity search algorithm and maybe some k nearest, and of course, index you need to do, and off you go. And for us developers, especially when you start out with AI, Postgres, I think most of you are familiar with, has a nice extension, pgvector, which allows us to work with vectors. And this is what we're going to do next. So now we're going to ingest our menu into a Postgres database. And of course, I'm using, again, my Kotlin notebook. There's a very cool and powerful construct within Kotlin notebook. It's called a data frame, which is a bit a jack of all trades. So here I have my Italian delight dishes in CSV format, and I can right away see what's in that CSV. Name is tiramisu, dish name, category, and then some ingredients. The first thing I'm going to do is I'm creating documents out of this CSV, because the documents is actually the object I can feed to my ingester so that it vectorizes it. So what will be vectorized? That's actually what you see here, the content. And what I make out of content, it's totally up to me. I chose now to use the dish name, the category, the ingredients, up to you. Whatever you think should be similar like a prompt. Now I have a list of documents. Then I use some nice abstractions offered by LangChain4j. So I have here an abstraction for an embedding store, which is here pgvector. I have an embedding model, and then I can compose my ingester. We actually omit here one thing. What you can do with AI, and what also many companies do, is they ingest unstructured data, like PDFs, Word documents, Excels, and so on. And for this to work, you need to kind of chop off all these texts in these PDFs or in these other unstructured documents. So for that, you have so-called document splitters. And it's actually a field of expertise by its own to split documents in such a way that you get the desired results. And LangChain4j has quite good splitters. But for our case, we don't need it because we already created documents ourselves. OK, so then I would say, let's start ingesting our documents into our Postgres database with this PG extension. That's what you can see here. So I have this table vector store. And what we see here is also this index. So access method HNSW. If you remember correctly, that was the index. It's an embedding. So all these kind of aspects just are easily visible. I can again use a data frame to query a database. That's it, check of all trades. Just give it some configuration and a query, and off we go. And now we see that the text I created have now gotten a vector representation. And now comes the cool thing, what we really want. We now can do our similarity search. Works quite simple. This would be my prompt, which I first vectorize. Simply use the exact same embedding model to create a vector representation, which I would use as an input here. And from there on, at least for Postgres, it's just plain SQL with a very special operator, this one here. Because this one stands for cosine similarity search. And there are others available, like the inner product, L1 distance, just more or less doing the same thing with slight differences. Cosine is the one you hear most, at least when you start with the field. Now we could say, OK, give me all the dishes that are similar to my prompt or have a similarity of 0.8. Most similar would be 1, least similar would be 0. And let's see if we can get something bad. Indeed, we get 2 dishes. If I, of course, lower the results, then I get more dishes back. And it's very important to realize that this aspect by itself can be very valuable. You don't really necessarily talk to LLMs. Only vectorizing data can already fill in quite a few valuable use cases in the enterprise, something we couldn't do before. OK. So then I think it's time to create our chat application. Before we create it, we need to understand a bit more about prompts, at least the format that is sent to an LLM. It's not actually the text that is sent. It's a structured JSON document that is sent to the LLM that consists of different sections. So the first section would be the role system, which actually gives guidance to the LLM how he has to handle the conversation. The second would be the user input, which is what the user types and maybe some stuffing additions, like your lookup from a rack system. This is then what you would send to the LLM, and the LLM would reply in the role of assistant. Then what you also see are things like tools, but these we're going to leave for now a bit for later. What's also very important to realize and also be aware of is that an LLM, if you just would send it prompt by prompt, it wouldn't keep track of history. So it would not be able to reason what you said before. So that's why you actually have to send a large part of the whole history of the conversation yourself. So this is simply the history of what happened before, often starting with system. That's the very first message. Then user assistant, user assistant. So we had already 2 interactions. And then the last would be the last interaction that is available. OK, so let's make that happen. For this, we're going back to our Spring controller and introduce our basic chat. So what you see here is we have also this system building block for our system prompt, which demands a bit of prompt engineering, which actually is a very silly term, because there's really nothing about engineering with prompt engineering. It's just plain trial and error. And LLMs can help you to make your prompts a bit more decent, but it's just try, see, I hate this, I add that, and so on, and so on. So here you see that the prompt I created, the system prompt created is, you're an Italian waiter, you're friendly, always answer in English, because all of a sudden it started talking Italian. So I had to add, you have to talk in English. And that, for quite some time it went well, and all of a sudden it was Italian. Then you just give some instructions. This is how you start. You say, welcome to Italian Delight. What is your chapter? So you have to order food for a person. And here you say, for these suggestions, you have to use the context in your prompt, so in this dish context. So this is kind of how you program LLMs. Then what we do next, or actually first, is we look for similar dishes based on our prompt input. And for this, Spring Boot has those vector stores, which it nicely abstracts, and with just some configuration, you would automatically get the PG vector libraries, extensions, and so on. So if you have enough configuration, then the vector store is actually taken care for you. And here we then create our prompt. What we don't have now are some ingredients for our chat history. So how does it preserve and send our history along? For this, I need to adjust my client a bit. So here I only have a logger, but I also actually need to provide this beast here, a message chat memory advisor. So chat memory can be persistent or in memory. In a real application, I would strongly suggest you to make it persistent, but for this use case, in memory is sufficient. And here I have this advisor, again, intercepting replies and requests. In order to make this fully work, what we need to add is this portion here. So we need to tell that this is some sort of conversation key, a bit like a session ID you used in old applications. And based on that ID, it would look up what you already used as interaction with LM and add this up to 50 elements. That's what I configured here. And with that, I think, well, we should be able to at least do a decent selection. So what I created here is a simple command line client that talks via HTTP with my API. It says hi, and you see it replies the way I would have expected it. I want to order this particular dish. It would list that dish, and that's actually our first step in our order flow, making use of RAG. OK, so far, so good. What we cannot do yet, now we can kind of look at options and then figure out what we want for our meal, but what we cannot do yet is order the dish. Because for this, I would have to make the LM call my APIs, right? It's a black box interaction, so somehow the LM should decide when to do that. Which leads us to the last very powerful and quite important part of this whole AI universe, for which right now many large investments are made. So the stakes, but also the expectations are very high with the field of LLM agents, which are actually BPMS, so business process management engines, on steroids. And as said, with what we've seen before with LLMs and their reasoning capability, this could also turn out to be BPMS on drugs, depending on how it works. So how does this interaction take place? Again, it's not hard conceptually. You have a prompt, and alongside this prompt, you would send some tools. That's the name they gave to it. What the heck is a tool? Well, a tool is basically everything a computer can call, right? It could be an API. It could be a web search like Wikipedia, a database lookup, file system, whatever. Alongside with the tool, you also say that this tool has this function. And then the LM can reason, OK, I'm now in a state that I think now it's time to call tool number 1. Instead of giving the answer back to the user, the chat application would intercept that reply where the LM says, hey, now you should call tool number 1. This is what you have to do then as application. So you'd have to take action, call this tool. LM would even fill in the whole request for you. So it just is a matter of passing that information through. Once you have a reply from your tool, you also would pass it to LM because it might be a failure or success. So the LM could reason again how it should proceed. And once that is done, well, our whole interaction has been completed. So let's program that in our application. Then I hope that we can, because it's already almost 6 o'clock, order a dish. So we have something to eat tonight. So the first thing we have to do is actually extend our system prompt, because I want it to be clear that it should call this order service once a user has ordered something. And what I also would like to include is that it should give a summary of the order and also the time indication which is returned by my order service. So how does this order service look like? That's quite simple. It's a function, a classical Java function, with a pocho as input and a pocho as output. That's it. Then I register this function as a bean, and I give it a description. Sometimes it's enough to only give the description, not adjust your system prompt, but I found that without my system prompt, it didn't do what I want. So also here, trial and error till you make it work. Then the only thing we have to do is, in our chat client, also tell that you have this function available. So I also can have many of them doing different things. For now, I only keep it at one. OK, so let's see how this is going to look like. Again, I have my chat client. I'm going to choose a meal like I did before. And then when I've chosen a meal, I expect actually this function being called. Now comes the big moment. I go for option 4. So let's see. It says, you've chosen spaghetti amatriciana. Your order will be ready in approximately 20 minutes. OK, interesting. Now let's look in the logs whether our service was called. And yes, it was called. So our order has now been completed. When we look at what the LLM replied, it's kind of interesting to look at that too. So here we get our response, and then we see in this tools call, in the reply, saying that now you have to call this order service with these arguments, meals, spaghetti, amatriciana. And of course, this can be whatever entity you put in with IDs and so on. OK, well, if we really try to replace this system from McDonald's with ours, then we still want the system to be able to talk, right? Not that users have to type human language. And again, with OpenAI, that's really something very simple to achieve. So the only thing you have to do is use a speech model that converts your text to speech. So we're now calling the same endpoint like here for simplicity, but then convert the text output we get into speech using one of the OpenAI audio models. Also, this particular model is only available for OpenAI. The Mistral model which you've seen before wouldn't be able to do that. So transcription is something it cannot do. OpenAI can. And then we get actually to our final demo, which, let's see, hopefully something you will hear to whet your appetite a bit, so my client also can play audio. You see, it takes...
Welcome to Italian Delight. How can I help you today?
We get a response. That's what you see in the logs now. And to create the transcription also takes quite some time.
Based on your preferences. Here are 3 dishes that feature tomato sauce and cheese. 1, pizza, a classic with tomato puree and mozzarella cheese. 2, spaghetti alla puttanesca, a flavorful spaghetti dish with canned peeled tomatoes, though it doesn't have mozzarella or mushrooms. 3, spaghetti amatriciana, another spaghetti option with peeled tomatoes and pecorino cheese, but no mozzarella or mushrooms. Would you like to go with the pizza, or would you prefer one of the spaghetti dishes? Let me know.
So, what do you want? OK, I make a choice for you. Number 3. And now the whole ordering should take place, and we get our final response.
You ordered the spaghetti amatriciana. Your meal will be ready in approximately 20 minutes. Thank you for your order.
And by that, I think we've implemented or replaced, hopefully, parts of McDonald's AI system with Italian Delight. So let's come to the verdict of the 2 frameworks used so far. When you look at LangChain, what I really like about it is that it's very modular and customizable. Spring has, again, a lot of magic involved. In the beginnings, you get weird errors, and then you have to kind of figure out what's going on. But once you have that more or less under control, it's also very convenient to use. So personally, I didn't redevelop a preference for one or the other. What's definitely sure is that LangChain4j is also applicable or usable in other applications than Spring. You can use it in Spring, but also in all the others, like Quarkus, Micronaut, and so on. But considering the fact that Spring Boot has about 90% of the market share, well, Spring AI still might be the most convenient option, even though you still can use certain tools from LangChain4j. What I found in terms of feature set, they're kind of feature parity. The only thing I found is that document splits are a bit more advanced. We haven't looked at those, but if this is a use case you're interested in, you can take a look at that. And also they have some capabilities to do RAG routing. So when you have multiple of these data sources, not only a menu, but maybe something in a total different context, you also need to decide which RAG source you need to call. Spring AI, I found that it can do transcription. LangChain4j cannot do that yet. And also the multimodal support is quite better. LangChain4j has great documentation samples. So if you look at the test section of LangChain4j, once you understand these concepts, you can quite quickly see how you can solve a use case like the one I showed you. And the Spring documentation is just, as the rest, on a very high level. Well, with that, I hope that the waves in our swimming pool of software development have soothed again, and that with some pizza we've ordered from our new system, we can look out with confidence to what the future holds as AI grows. Thank you.